An introduction to magnetic fields and forces is going to be the topic of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. Now in this lesson, we're going to start by taking a look at a simple bar magnet. We'll use that to introduce magnetic fields, we'll kind of trace them, and we'll see some similarities to the electric dipole we saw in the last chapter. And then we're going to take a look at the magnetic force acting on a charge in motion in the associated calculations. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So we're going to start this lesson off by taking a look at the magnetic field lines around a simple bar magnet like this one. And every bar magnet is what we call a magnetic dipole. It has two poles every time. You've got a magnetic north pole and a magnetic south pole. Those are the labels we give to them. They're kind of opposite poles, if you will. And it turns out, even if I cut this magnet in half and create two smaller pieces, each of those pieces will also have a magnetic north and a magnetic south. And if I cut those pieces in half, each of the new pieces will have a magnetic north and a magnetic south, and you can keep going on. So it turns out that every bar magnet is going to have a magnetic north and a magnetic south pole every time. Now, in drawing the magnetic field lines, it's instructive to go back and remind ourselves of what the electric field lines looked like with an electric dipole. Now, with an electric dipole, it's a little bit different because we actually have separate point charges, where with our bar magnet here, it's one piece of metal or ferromagnetic material, as the case may be, that has a north and a south pole built into that single piece of metal. But you might remind yourself, and ask you a question, all electric field lines originate where and terminate where? Well, they all originate either on a positive charge or from infinity, and terminate either on a negative charge or at infinity. So in this case, with the electric dipole, the electric field lines always go from positive to negative. And we're going to find that the magnetic field lines around a bar magnet look very similar. And they always go from north to south, sort of, as we'll see. So it's going to look very similar here, though, but we're going to start with north and work our way around to south. Same thing around the other side here. And we can make bigger field lines just like we did with the electric dipole as well. And now we're going to see the one exception, though, is that there's actually there's actually magnetic field lines going right through the bar magnet as well, but from south to north. And so here's where we got to be careful. If we said, where do the electric field lines run in an electric dipole? Well, always from positive to negative, period, no exceptions. But if we said, where do the magnetic field lines run around a bar magnet? So as long as we're talking around the bar magnet, outside of the magnet, it's from north to south. But if we talk about through the magnet itself, it's from south to north. And so we got to be careful, one, how we ask that question, but two, how you answer that question and figure out which question you're really being asked. Are you asked about the magnetic field lines around a magnet or within the magnet? So be careful with that. So let's next take a look at the interaction between two of these lovely bar magnets. So I've got two identical ones here. And so it turns out that just with, like we saw with electric charges, like charges repel and opposites attract, the same is going to be true of magnets and their corresponding poles. So if I try to line up north pole with north pole, there's a repulsion here. They do not want to stick whatsoever. Same thing with south pole and south pole. But if I take and line up north to south, they stick. And it works either way. If I flip them both over and still line up south to north, they're still going to stick. And now there's an attraction instead of a repulsion. Same thing if I try to line them up lengthwise instead of end to end. Again, if I line up south to south, north to north, they repel each other. They don't want to stick at all. So, but if I flip it around, all of a sudden now, and they stick yet again as well. Now, why do we call them north and south? Well, it turns out if you take a ferromagnetic material like this one again, so let's say I tie a string around the metal and just kind of rotate, we'll find out that the north magnetic pole here always wants to point somewhat in the northern direction towards the north pole of the Earth. Well, it turns out it's not exactly at the geographic north pole of the Earth. It turns out it is somewhere in the northern Hudson Bay or something like that. But we'll get there in a minute. So, and if instead of tying a string here, maybe you just want to take a piece of styrofoam and float it in water and set this right on the styrofoam, well, the styrofoam will rotate until, again, the north pole end of the magnet points towards the north pole, if you will, points north. Well, again, if you recall how this lines up with our other magnet, so it wants to line up with the other magnet, north to south, south to north. Well, it turns out it's interacting with the Earth's magnetic field when it kind of swivels around so that the North Pole points to the north. And the Earth's magnetic field, it's as if the Earth has a big fat bar magnet in its core running across the Earth in a north to south fashion, approximately, if you will. Well, if the north end of this magnet is pointing towards the North Pole, well, then the Earth's bar magnet must have a south pole up at the north end. Well, this is getting confusing. So it turns out what we call the geographic North Pole is actually the magnetic South Pole. And what we call the geographic South Pole down in Antarctica is actually a magnetic North Pole. So it's kind of backwards. And so some people might have properly called this the north-seeking pole of a magnet, and this is the south-seeking pole of the magnet or something like this. But it turns out they're named for historical reasons, and we're stuck with them now at this point. And once again, it also turns out that the geographic North Pole is not the same as the magnetic South Pole. The magnetic South Pole is not all the way at the North Pole of the Earth. It's actually, again, in the northern Hudson Bay. So, and the geographic South Pole is not the same as the magnetic North Pole. The magnetic North Pole, it turns out, is off the coast of Antarctica somewhere, not kind of in the center of Antarctica. So, and it turns out those are moving around a little bit as well. And it turns out we don't know exactly why the Earth has a magnetic field. Now, you might be like, well, maybe there's a big iron bar magnet in the core of the Earth. So, and the problem with that is that we believe we have good evidence that the core of the Earth is actually melted liquid, and iron, fair amount of iron in there, but not solid. And that's a problem. So the reason this lovely substance right here is magnetized is that all the little localized regions in this lovely bar magnet are pointing a certain direction, if you will. Their magnetic moments are aligned to point a certain direction. So, and by doing that, iron's a good ferromagnetic material. So, but not all iron has been magnetized. But if you put it in the proximity of a magnet for a long period of time, it might get magnetized. Or if you scrape a magnet so over and over and over again against a piece of iron, it might become magnetized. And the idea is that you're aligning the different localized magnetic moments in such a way. And it turns out at elevated temperatures, you get more mobility of the localized regions, and so it's easier to magnetize, a ferromagnetic substance and stuff like that. So, but it's still in the solid phase is the key, though, and so they can permanently freeze with their magnetic moments more aligned in a certain direction. Well, the problem, if the Earth's core is liquid, there's no way to permanently freeze those magnetic moments in a certain direction. So, well, it turns out we're going to find out that electric currents result in magnetic fields, and we kind of suspect that maybe then there's an electric current running through the Earth's core in some way, shape, or form. And what the nature of that current is and what causes it and stuff, we don't actually know. But we do know that it's not fixed either. So it is changing over time, and as a result, both the location of the magnetic North Pole and the magnetic South Pole, those are changing a little bit over time as well. And there's evidence to show that they actually will reverse in polarity every so many million years or something like this as well. So let's go back and again do a quick review of electric fields, and then we'll compare magnetic fields to those. So I just want to go back and review real quick. The direction of the force of a particle in an electric field. And if you recall, what must a particle have to feel a force in an electric field? Well, it must be charged. So, and the magnitude of the force is going to equal Q times the magnitude of the electric field. And so if I have this positive charge right here in this electric field, what would be the direction of the force that it's going to feel? Well, for a positive charge, it's in the same direction as the electric field. So, well, what if I swap that positive charge out and now make it a negative charge instead? Well, for a negative charge, the force is in the opposite direction. It's always in the opposite direction as the electric field. So in this case, the force would be pointing down. So for a positive charge, the force is in the same direction as the electric field. For a negative charge, it's in the opposite direction. Cool. So, but the only thing a particle must have in order to feel this force is charge. Well, let's swap some things out here. So one, let's go back and start with a positive charge again. So, but let's make this, instead of an electric field, now let's make it a magnetic field. So it turns out the symbol for magnetic field is B. So it will be measured in Tesla as the SI unit. We'll find out that Gauss is pretty common as well, because a Tesla is pretty big. There's 10 to the 4th Gauss equal to 1 Tesla. But the Tesla is the SI unit. All right, so it turns out the equation relating the force to the magnetic field for a particle is a little more complex, and there's a little more to it than this, which we'll add in a little bit here, but it's qvB. And this is going to give us some intuition here that it means that for a particle to feel this force in a magnetic field, it must be charged and it must have a velocity. It must be moving. So if I've got this positive charge just sitting here in this magnetic field, well, if it's just sitting there, that means the velocity is 0, which means the force is 0, and it will not feel a force at all. So we talk about the force on a charge in motion for magnetism here. It has to be in motion. If the charge here is not moving, it will not feel a magnetic force. That was not true for an electric force. It is going to be true for the magnetic force. And again, this is not intuitive. It's just something we have discovered. All right, now it turns out there's a little more to this as well. It turns out there's a little factor of sine theta on here as well, where theta is going to be the angle between the velocity vector and the magnetic field vector. And it turns out, well, if you recall, the sine of 0 is 0 and the sine of 180 is 0. And the sine of 90 is 1. So keep that in mind for just a second. So if I start drawing in a velocity vector here, and let's say I say that this charge right here is moving straight up, perfectly parallel with the magnetic field. Well, that would mean the angle between the velocity and the magnetic field would be 0, and the sine of 0 is also 0. And so it turns out if your velocity and magnetic field are parallel, there is no magnetic force there either. So it's not just enough that it's moving. It turns out that some component of the velocity must be perpendicular to the magnetic field, even just the slightest component. Well, if it's parallel with it, there is no component of the velocity that's perpendicular to the magnetic field. Same thing if we switch that around and make that velocity point exactly the opposite direction here. And now it's anti-parallel with the magnetic field, but again, that's also a condition where there is no component that is perpendicular to the magnetic field. And once again, the magnetic force would be 0. And again, the sine of 180 degrees with it being anti-parallel is also 0. All right. It turns out that the sine function reaches a maximum at 90 degrees, and the magnetic force, therefore, also reaches a maximum at 90 degrees as well. Now notice there are some options for 90 degrees here. I could put it to the right, I could put it to the left, but we don't live in just a two-dimensional world, we live in a three-dimensional world. And so it turns out anywhere in this horizontal plane that I direct it, whether it's out of the board, into the board, left, right, or anything in between, as long as it's in this horizontal plane, will end up being perpendicular to the magnetic field and will reach a maximum of the force. And here's where things are going to get just a little bit crazy. So it turns out this is the result of what we call a cross product. And for an algebra-based course, you definitely don't have to know what a cross product is. It's usually something you encounter a little bit with matrix algebra, and maybe you get it in a college algebra class, but you might get it in a straight up matrix algebra course as well. But that's where this ultimately comes from. And it turns out with a cross product, figuring out the direction of a cross product, well, it turns out it's going to be orthogonal to both components of the cross product. Well, what that ultimately means, in this case, the components of the cross product are the velocity and the magnetic field, and our force in this case is going to be perpendicular to both of those. Well, right now, they form a plane. The velocity and the magnetic field form a plane, and that plane is the plane of the board. To be perpendicular to that plane of the board, you either have to be coming straight out of the board or going straight into the board. And it turns out your force is always going to be mutually perpendicular to both the velocity and the magnetic field. All right, now which one is it? And how do we figure that out? Well, it turns out we come up with what we call the right-hand rules for figuring this out. And keep in mind, they are right-hand rules. Be careful about accidentally pulling out your left hand and things of a sort, as we'll see. But they are the right-hand rules, and we use them as kind of just ways of figuring out the direction of the force based on the given directions here. And so the way this is going to work, there's unfortunately multiple ways of presenting these right-hand rules, and my apology for that. It's just the way that it is. I'm going to present one. I might allude to some others that maybe it's presented for you. If you've got a way that you've already learned it and stuff like that, and you've got it, kind of foundationally in your head already, run with it. Don't use mine. But if you haven't got one in your head and you want a good set, mine's as good as any out there. All right, way this is going to work. You're going to line up your fingers with the magnetic field. You're going to line up your thumb with the velocity, and then the force is going to come out of your palm. So let's see how this works here with this particular example right here. So in this case, you want to point your fingers in the direction of the magnetic field. So they're pointing straight up, so where the magnetic field points. But then you want your thumb to point in the direction of the velocity. So I had to flip it around, pointing to the right. And in this case, then the force is going to come out your palm, which in this case means it's coming straight out of the board. Now, this is not the only way people do this. Some people do this instead of doing a straight open hand like this, they'll kind of make it like a gun, and they'll say finger in the direction, so index finger in the direction of the magnetic field, so thumb still in the direction of the velocity, and then your middle finger is going to point perpendicular to both of these and point straight out. Well, that's the same thing as your palm. So either way, those are functionally equivalent. Now, some people will do this a little bit different. They'll say, well, if it's really a cross product of V cross B, and if it's V cross B, you need to start off first with your fingers pointing towards V and then curl them up to B, and then whichever way your thumb points, that's the direction of the force. So, and that works too. And it's consistent, it's reliable, and truth be told, in a matrix algebra class, that's often how cross products are taught. So, however, that is not the convention I'm going to be using, so I will not allude to that from here on out. So, it turns out we're going to learn like 4 different right-hand rules for different scenarios in magnetism here in this chapter, and I'm going to be as consistent as I can with possible, where my fingers are going to point in the direction of the magnetic field, and I'm going to have a velocity of some sort, as we'll see with my thumb, and we'll go from there. All right, so what if this had been a negative charge instead? So, well, with a negative charge, just like in an electric field, the force felt by a positive charge in an electric field is in the opposite direction as a force felt by a negative charge. And the same is true for the magnetic force as well. And so in this case, if you point, again, your fingers in the direction of the magnetic field, your thumb in the direction of the velocity, well, for a positive charge, the force comes out the palm, which means for a negative charge, it goes the opposite direction out the back of your hand and into the board instead. All right, now it turns out that you can also decide to use a left-hand rule for this one as well. And if you use your left hand for a negative charge, well, then the force would still come out your palm, and you'd have your fingers up, your velocity to the right, and then the force would still be coming out the palm because you're using your left hand instead, and it gives you the opposite result. I hate that just with a passion. I had a student one time who just almost, just instinctively always pulled out his left-handed to do the right-hand rule. And so I hate giving students an option of ever using a left-hand rule. And so I like just saying, hey, do the right-hand rule. If it's a positive charge, it comes out your palm. If it's a negative charge, it's just the exact opposite direction, 180 degrees. So now we're going to take a look at 3 different applications of the right-hand rule. And in the first one, we got a positive charge. It's going to be moving to the left, and it's going to enter a magnetic field that's directed upward. And the question is, what is the direction of the force? And so in this case, again, we're going to line up our fingers in the direction of the magnetic field. Notice we got a lot of options of which way we can rotate it that all have my fingers pointing up, but we need our thumb to point to the left. And for a positive charge, again, the force comes out the palm, which is into the board in this case. So I'm going to write into the page, because you're most likely going to see this, into the screen or into the page of a book or something like that, or into the board in this case. So for the next one, for a negative charge, it would work exactly the same way. And again, make sure you're using the right hand. So fingers in the direction of the magnetic field, thumb in the direction of the velocity. But instead of coming out the palm, for a negative charge, it's the opposite direction coming out the back of the hand, which would now be out of the page. Okay, so similar to the ones we saw. Now, we live in a 3-dimensional world, and all of these are inherently 3-dimensional problems. And so what if your magnetic field or your velocity, instead of being up, down, left, or right, is either coming out of the page itself or into the page? We need a way to represent that. And it turns out that for something out of the page, it's represented by a dot, or by a dot with a circle around it, same diff. Those mean directly out of the page coming out towards you. So, and then it turns out going into the page is represented by an X, like it's the tail of an arrow going into the board, so to speak. And it's either an X or it's an X, once again, with a circle around it. Either of those would mean something is being directed straight into the board. All right, so in this next example here, we've got a positive charge with a velocity that's pointing up, encountering a magnetic field that is directed out of the board. And so if we apply our right-hand rule, so first thing, I'm going to have to get my fingers pointing out this direction in some way, shape, or form out of the board. So, and then I need my thumb to point up. And so my hand is going to be oriented in just such a fashion with the magnetic force coming out the palm for a positive charge and directed off to the right in this case. So you can see why this is sometimes rather humorous when you see students taking the test on this particular material, and all over the room you could look around and students are kind of like, tweaked and contorted into various positions and stuff like this, trying to do these right-hand rules, and it'd be a little bit of a pain in the butt, but you really want to make sure you've got this down pat and get a lot of practice. So with the directions on the right-hand rules, but also with calculations, which is what we'll do next. So this diagram is included with the question we'll be solving here. It's right on the study guide, part of the question, definitely needs to be given. And the question says, when the 1.0 microcoulomb positive charge in the diagram enters the region with the 2.0 Tesla magnetic field directed into the page with a velocity of 1200 meters per second directed to the right, what is the magnitude of the magnetic force acting on it, and what is the initial direction of the magnetic force? All right, so in this case, with the magnetic field being directed into the page, or into the board in this case, and the velocity pointing to the right, they are 90 degrees apart. And the sine of 90 is 1. And so the force here is going to be at a maximum. So we've got F equals Q, that's not a V, V, B, sine theta. And in this case, sine of 90 is 1. So that term's going to kind of fall off here. And so F equals Q, and that 1 microcoulomb is going to be 1.0 times 10 to the negative 6 coulombs. Velocity, 1200 meters per second. So, and then finally the magnetic field, 2.0 Tesla. That's a rather strong magnetic field. The Earth's magnetic field is like 0.5 Gauss. And if you recall, there are 10,000 Gauss in 1 Tesla. So 2 Tesla is pretty significant, significantly stronger, like 20,000 times stronger than the Earth's magnetic field. All right, but plug and chug from here, and we can do this probably in our head here. So 1200 times 2 is 2400, which is 2.4 times 10 to the third, and then times 1 times 10 to the minus 6 would be 2.4 times 10 to the minus 3. And this is going to come out in newtons. If we use SI units all the way across, then the SI unit for force will just kind of fall right out. We could also write this as 0.0024 newtons as well. So that's the first part of the calculations. What is the magnitude of the force? And the second part of the question is, what is the initial direction of the force? In this case, that's where the right-hand rule is going to come into play. And we want to point our fingers in the direction of the magnetic field. That means into the board. And we want to point our thumb in the direction of the velocity, which means I'm going to have to orient it in such fashion like so. And coming out my palm for a positive charge would be a magnetic force that is going to be directed upward. So at least it is initially. So keep in mind, so once we get this positive charge in here, it's going to have an upward force acting on it. And that's going to change its trajectory. And this thing's going to start veering off upward. But as it veers off upward, that's going to change our right-hand rule as well. If the direction of the velocity changes, then your application of the right-hand rule is going to change as well. And so once again, the magnetic field isn't changing. But instead of my thumb pointing to the right, as this thing starts to change its trajectory, my thumb's going to move up there as well. And the force is going to change direction as well coming out my palm. And it's going to change direction all the time. And what we'll find out is if this region of the magnetic field is big enough, you'll probably get to a point, or you potentially could get to a point where it just starts doing circles in the magnetic field. And the whole time, as it changes, there's going to be a force directed towards the center of that circle at all points. So, and with uniform circular motion, the force responsible for keeping it on that circular path, you might recall, is the centripetal force. So we got a couple of different ways this might be taken a step further. So we calculated the magnitude of the force. You might get a question that says, well, if you calculate the magnitude of the force, if I give you the mass, then what's the acceleration? And you would just use Newton's second law and say F equals ma, and plug in the mass in kilograms and use the force we just calculated, and then you could solve for the acceleration. The other way it could go is it might go and once again give you the mass of the particle and stuff like that. It might say, what's the radius of the circular motion after it enters the region with the magnetic field? Well, in that case, you'd want to say, well, okay, sum of the forces, instead of equaling ma, when there's circular motion, it equals the centripetal force of mv squared over r, as you might recall. And so in this first example, we'd be setting qvB sine theta equal to ma. So in the second case, we'd be setting qvBsin theta equal to mv squared over r. So, and again, provided we were given the mass, so we were already provided with the magnitude of the velocity, we could solve for the radius of that circular motion as well. So just a couple of examples of how this could be taken a step further in a calculation. If you found this lesson helpful, consider giving it a like. Happy studying.